Hello everyone, welcome to the seminar. My name is Mark Blonquist from Apogee Instruments in Logan, Utah. I'm going to speak about plant canopy water status estimation from canopy temperature measurements. But before getting that far, I'm going to spend a fair amount of time talking about actually measuring surface temperature. This slide provides a brief outline of where the presentation's going. So first I'll talk about infrared radiometers, their operation and calibration, and then surface temperature measurement, specifically correcting for surface emissivity and field of view. I'll also deal with the challenge of partial canopy cover. The two methods I'll talk about to handle that are angling radiometers and then a model to account for soil temperature. And then finally we'll get to estimating canopy water status. We'll spend some time with the simpler method, the crop water stress index, and then a more involved method, canopy stomato conductance. So the basic components of an infrared radiometer are the radiation detector itself, an internal temperature sensor to provide a temperature measurement of the detector, and then a housing to hold it all together. The signal generated by the radiation detector is proportional to the difference between the radiation being absorbed by the detector and also the radiation being emitted by the detector. So all surfaces or objects that have a temperature above absolute zero emit infrared radiation. The detector in the radiometer is absorbing the radiation that's emitted towards it. At the same time, the detector is emitting radiation. So the signal will be dependent on the difference between these two radiation streams. When the absorbed radiation at the detector is less than the emitted radiation, the signal is negative. When the absorbed radiation at the detector is greater than the emitted radiation, the signal is positive. So the sensor is actually measuring or detecting radiation, but temperature is the quantity that we're interested in. And of course, they're related through the Stefan-Boltzmann law, where energy is proportional to a constant times the fourth power of temperature. Another important component, an essential component of the radiation detector itself is a filter to block all wavelengths outside of what we call the atmospheric window. So the plot you're looking at here shows wavelength on the x-axis and atmospheric transmittance on the y-axis. The wavelengths between 8 and 14 micron or micrometers is defined as the atmospheric window because at these wavelengths the transmission of the atmosphere is very near 1, meaning the atmosphere is transparent like a window. The filter on the radiation detector needs to closely correspond to the atmospheric window to eliminate influence from the atmosphere, or essentially see through the atmosphere to the surface that we're interested in measuring. Below 8 micron, we can have interference from water vapor, and above 14 micron, we can have interference from CO2. The final component that's essential for infrared radiometer is the calibration. The photo that you're viewing now is a picture of the calibration system at Apogee Instruments. So there's two main components. The one that I've circled here is the actual cap piece where all the radiometers are held during the calibration procedure. The cap piece is mounted on top of this piece here, which is the actual blackbody cone or radiation source. What happens during calibration is the radiometers are mounted in the cap piece over top of the cone, and you can see some insulation around the cone there. So with the two independent pieces, the cap and the cone piece, we can maintain their temperatures independent of each other, and then we can collect a whole data set across a whole range of temperatures. And during the calibration procedure, we also collect the millivolt signals from the radiometers. Produces a large data set that we can then use to derive custom coefficients for all radiometers that allow us to convert the signal, which again from the previous slide was proportional to the radiation difference. we can convert that to a temperature. Once we have a calibrated radiometer, we're ready to deploy it in the field and start making measurements. Surface temperature measurements are pretty straightforward when the surface is a black body. A black body is defined as any object or material that emits the theoretical maximum amount of radiation based on its temperature. Or we define it as an object or material with an emissivity equal to 1, where emissivity is just the fraction of black body emission. So here I have a plant canopy with emissivity equal to 1. In that scenario, the target temperature returned by the radiometer would equal the true surface temperature. But in practice, natural surfaces are not black bodies. Most plant canopies have emissivities equal to 0.98 or 0.99. What that means is the plant canopy will be emitting 98 or 99% of the theoretical maximum based on temperature. And there'll be a small fraction of background radiation that's directed towards the radiometer because it's reflected from the surface. So surface reflectance is equal to 1 minus the emissivity, or in our case it would be 1 minus 0.98. So essentially what this means is if we deploy a radiometer to measure a plant canopy in an outdoor environment, the background is the sky. The sky is emitting infrared radiation just like the plant canopy. And where the plant canopy is not a perfect black body with an emissivity equal to 1, a smaller fraction, 1 minus the emissivity of the background radiation, in this case coming from the sky, is reflected from the plant canopy and directed towards the radiometer. Typically, the sky temperature and the surface temperature are much different, and so we have to account for this reflected fraction in order to get accurate measurement of the surface temperature. In order to do so, we need an estimate or measurement of the surface emissivity, an estimate or measurement of the radiation coming from the sky, in addition to our measurement of the surface temperature. So I'm not going to go through the derivation of the equation to correct for emissivity, but I'm showing it here. So we take our measurement of target temperature and we input it along with our measurement or estimate of emissivity and our measurement or estimate of the background temperature. Then we can calculate the actual or true surface temperature. To give you an idea of the magnitude of effective emissivity, have a couple simple examples, one for a clear day and one for a cloudy day. So let's assume that our sensor is measuring a temperature of 25 Celsius. A pretty standard background temperature or sky temperature for a clear day would be negative 40 Celsius. Again, our canopy emissivity is 0.98. And when we plug all those numbers into the equation above, we get a surface temperature almost a full degree warmer than the temperature we measure with the radiometer. On a cloudy day, the background temperature is much warmer. It's a lot closer to the actual measured surface temperature. And when we plug the numbers into our equation above for a cloudy day, we find that the surface temperature is much closer to the measured temperature. Here we have a table listing emissivities for several different surfaces one would encounter in natural settings, plants, soils, water, and so forth. You can see that most natural surfaces are near black bodies with emissivities in the 0.9 range. But we can find some things that are very, very low emissivity, like polished aluminum, for example. I also have at the bottom of the slide some typical values for the background temperature, or be sky temperatures in an environmental application. Clear sky is often very cold, negative 40 to negative 60 C. Overcast sky is often near air temperature. I've also listed a simple equation that you can use to calculate sky temperature. It's approximated from the air temperature, where we take air temperature plus 50 times the fraction of clouds minus 60. So on a clear day, our fraction of clouds would be 0, and this equation would simplify to air temperature minus 60 is equal to the sky temperature. On a completely overcast day, our fraction of clouds would be 1. This equation would simplify to air temperature minus 10 would be equal to sky temperature on an overcast day. So this can be used for a simple way to approximate sky temperature used with emissivity correction. Moving on from emissivity, another important consideration is the area of surface that the radiometer actually views, or in other words, the field of view. So I like to draw an analogy whenever I explain field of view of an infrared radiometer. And the best analogy that I can think of is put yourself in front of a flat wall in a dark room with a flashlight. If you hold the flashlight perpendicular to the wall and turn on the flashlight, you'll see a circle of light. As you move the flashlight closer to the wall, the circle gets smaller, and as you move the flashlight away from the wall, the circle gets larger. If you start to angle that flashlight so it's no longer perpendicular to the wall, then the circle of light spreads out into an ellipse. So the same principle holds for a radiometer that you direct towards a surface. If the radiometer is oriented perpendicular to the surface, then it's going to view or sense a circle. If the radiometer is close to the surface, it will be a small circle, and if the radiometer is moved further from the surface, it will be a larger circle. If you start angling it away from perpendicular, it will view an ellipse. And the area that being measured or sensed by the radiometer is dependent on 3 things: the field of view, the radiometer mounting height, and the radiometer mounting angle, where the field of view is just defined as the angle or half angle of the cone that's formed by the footprint that the radiometer sees, and then the apex of the cone here at the aperture. So companies should specify what the field of view of the radiometer is. In this example, it's a 22-degree half angle or a 44-degree full angle field of view. This slide shows multiple different models that are available from Apogee Instruments, and it lists their fields of view. I won't go into detail about calculating the field of view, but one very helpful tool that runs the calculations is found online, the website here. All you have to plug in this calculator are the 3 things I mentioned on the previous slide: the field of view specification in terms of the half angle, the distance of the radiometer from the target, and then the angle of the radiometer with respect to the target. And the calculator returns the dimensions of the ground area that the radiometer will be viewing or sensing, and also the area of the footprint. One of the challenges of measuring plant canopy temperature with an infrared radiometer is the situation where plant canopy doesn't occupy the entire field of view. Shown here in this example, plant canopy occupies part of the field of view, but the radiometer is also seeing some soil. In most situations, the soil temperature and plant canopy temperature are different, so in order to get an estimate of the canopy temperature, we have to account for the soil temperature somehow, or eliminate the soil from the field of view. One way to deal with this is to angle the radiometer such that we maximize canopy within the field of view. Doing this, it's very helpful to rely on the field of view calculator that I mentioned in the previous slide. It can provide estimates of the actual area being sensed by the radiometer. So another way to try to estimate plant canopy temperature when the surface is only partially covered by the canopy is to actually measure or estimate the soil's temperature and then approximate the fraction of canopy within the field of view of the radiometer and the fraction of soil within the field of view of the radiometer. Here again, I won't go through the derivation of this equation, but we can use this simple relationship with the measurement of the soil temperature, estimate of the fraction of surface that's soil, a fraction of surface that's canopy, and then the actual surface temperature that we measure with the radiometer, and calculate the canopy temperature. Once we have a measurement of actual canopy temperature, we're ready to progress to use that canopy temperature to estimate canopy water status. But before we go through the two methods that I mentioned in the introduction, I wanted to talk a little bit about the theory behind using canopy temperature as an indicator of water status. So plant leaves are actually covered with small microscopic pores called stomata. In order to photosynthesize, plants have to take up CO2. Stomata open in the presence of light in order to allow CO2 to enter for photosynthesis. An inevitable trade-off when stomata open is water loss. Plant leaves are saturated with water and the atmosphere is often dry, sometimes very dry. So water evaporates out of the stomata when they're open in order for CO2 uptake to occur. So plants uptake soil water to replace the water being lost through the stomata during photosynthetic uptake of CO2. And as plants draw down water in the soil and soil water becomes limiting, plant water uptake obviously starts to decline. This tends to close stomata. Stomatal closure reduces the stomatal aperture, or the degree of opening, and this in turn reduces the transpiration, or the evaporation of water from the stomata. Evaporation is a cooling process, so as stomata close in response to a drawdown of soil water, plants aren't as cool as they otherwise would be, so the canopy temperature thereby increases. One of the most important factors we have to remember, however, is that soil water status is not the only control on canopy temperature. Canopy temperature by itself is actually a poor indicator of plant water status because there's multiple factors that control canopy temperature. In addition to transpirational cooling, which is partially controlled by the soil water status, air temperature, humidity, radiation, and wind, all the environmental conditions that the plant is subject to will influence the canopy temperature. So in order to use canopy temperature as a means of estimating water status, we have to account for all of the variables that can influence it. So an early method, and a rather simple method for using canopy temperature to quantify water status, is called the Crop Water Stress Index, abbreviated CWSI. This method was developed by Idso and colleagues in 1981. At the end of the presentation, I'll provide the full citation for the paper that Idso and colleagues published. But essentially they found through their field data that the difference between canopy and air temperature for a well-watered canopy declined as vapor pressure deficit increased. They also found that this canopy to air temperature difference was relatively constant for a canopy experiencing significant water stress. So they used these two boundaries, what we're defining as a non-water stressed baseline and a water stressed baseline, as sort of reference points to compare actual measurements of canopy and air temperature. So here's the equation that they developed. The crop water stress index is the measurement of canopy minus air temperature minus the non-water stress baseline, then divided by the difference between the water stressed and non-water stressed baseline. So the required measurements in order to apply this empirically based crop water stress index are canopy temperature, air temperature, and relative humidity. The air temperature and humidity are required to calculate the vapor pressure deficit. So just to illustrate how the crop water stress index works, let's say our measured canopy minus air temperature value was 0 for a vapor pressure deficit of 3. We would then calculate the crop water stress index by taking the difference between this measured value and the non-water stress baseline, which we define as A, and then dividing that by the difference between the water stress baseline and the non-water stress baseline, which we define as B. So crop water stress index is just A over B, or in our example, we take our measured value of canopy minus air temperature of 0, subtract off the non-water stress baseline, and then divide the numerator by the difference between the water stress baseline and non-water stress baseline. And that gives us a crop water stress index of 0.46, or approximately halfway between the non-water stress and water stress baseline. The crop water stress index is actually designed to output a value of 0 when the measured value of canopy to air temperature falls on top of the non-water stress baseline, and it outputs a value of 1 when the measured value of canopy to air temperature falls on top of the water stress baseline. The major advantages of using the empirical crop water stress index are its simplicity. It only requires 3 measurements, and the measurement errors are calibrated out. Typically, the baselines are derived from field measurements, which allows for field calibration. The disadvantages are that empirical data is required to determine the non-water stress and water stress baselines. So we have to have some field collection data before we start. The alternative to this would be finding specific, crop-specific values of the non-water stress and water stress baseline in the literature. Another major disadvantage is the environmental conditions must be similar from 1 hour to the next if we're going to compare hourly values of crop water stress index, or from 1 day to the next if we're going to compare daily values of the crop water stress index. The reason being, we said in the previous slide that multiple factors beyond the amount of soil water available for plants to uptake control canopy temperature. Wind speed, radiation, air temperature, all of these variables will impact the canopy to air temperature difference. So if we have significantly different wind speed from 1 day to the next, or a significantly different radiation environment from 1 day to the next, this won't be accounted for in our baselines. It makes the empirical crop water stress index error prone. But to show how well the crop water stress index works, I have here 11 days of data collected over a cornfield near North Platte, Nebraska in the middle of July. In the upper graph, we're showing the canopy to air temperature difference, and in the lower graph, we're showing the crop water stress index. The green line is the non-water stress baseline, the red line is the water stress baseline, and the black line is the measured value of canopy to air temperature. You can see in the first couple days, the crop water stress index is quite low, but it tends to increase over the course of a few days before dropping back down again. Here the response going from a value near 0.5 or 0.6 back down to a value near 0 was caused by 20 millimeters of rainfall. So the crop water stress index behaves how we would expect. It increases as soil water is drawn down. When rain falls, it responds by decreasing to near 0 You can see near the end of this data set, it's starting to increase again, indicating water stress due to soil water drawdown. One more interesting point to make is that there is within-day variability. This may represent actual increase in the crop water stress index over the course of a day, or it might indicate variable environmental conditions. In addition to the empirical crop water stress index, Jackson and colleagues in 1981 also developed a theoretical or energy balance based version of the crop water stress index. So rather than relying on the empirically derived baselines, they took all of the equations describing the energy balance for the plant canopy, shown here in the diagram, and they combined them and rearranged them to solve for the canopy to air temperature difference. I won't combine the equations and show the TC minus TA equation, but what that gives you is a means of calculating the non-water stressed and water stressed baseline in real time, so that conditions don't have to be the same from hour to hour or day to day as required with the empirical crop water stress index. The drawback to this more theoretical or energy balanced based version is it requires a lot more data in order to actually get values of the crop water stress index. So in addition to canopy temperature, air temperature, and relative humidity, we also have to have a measurement or estimate of net radiation, a measurement of wind speed, and then measurements or estimates of canopy height and leaf area index. Well, I won't say anything more in this presentation about the theoretical version of the crop water stress index, but again at the end of the presentation I'll provide the reference to the paper in which it was derived. A method similar to the energy balanced based version of the crop water stress index is a direct calculation of the plant canopy stomatal conductance. So we can take the exact same plant canopy energy balance equations that were used to derive the theoretical crop water stress index, and we can combine them and rearrange them to solve for this term, the plant canopy stomatal conductance. Stomatal conductance is an actual quantification of the degree of stomatal opening or stomatal closure. So this calculation of plant canopy stomatal conductance has the advantage of being a physiological variable that's directly related to stomatal aperture. And it actually accounts for all variables influencing canopy temperature. So unlike the empirical crop water stress index, it should work well under all environmental conditions. So to demonstrate the calculation of canopy stomatal conductance, have the same data set for corn near North Platte, Nebraska. In the graph on the top, the black line is the actual canopy stomatal conductance calculated from the equation on the previous slide. And the green line is a value we're calling potential canopy stomatal conductance. It's derived from a leaf level model scaled up to the canopy. The details are found in the Blonquist et al. Paper referenced on the previous slide. I won't go into the nuts and bolts of the leaf level model, but I will provide the reference for the paper at the end of this slideshow. So a comparison of the actual to potential canopy stomatal conductance gives an index of water status. And you can see here the ratio starts out near 1 and then declines as the canopy draws down water from the soil. Just like we saw with the crop water stress index, it dropped to near 0 following a rainfall event. The ratio of actual to potential canopy conductance increases after the rainfall event, and then after a couple days being near 1, it starts to decline again as water stress sets back in. Also, like the crop water stress index, there is some within day variability of the ratio of actual to potential canopy conductance. This slide just provides an indication of how well the calculation of actual canopy conductance works. Here we're showing the values from the equation compared to potential values derived from a scaled up leaf level model for all days immediately following rainfall for the entire summer from a corn crop near North Platte, Nebraska. So the reason we're only showing data for days immediately following rainfall is we would expect the actual conductance to closely match the potential conductance under well-watered conditions. And indeed, that's what we find. The data match a one-to-one line relatively well. There are some outliers where the actual conductance is significantly higher than the potential conductance, and it's possible these are times when the canopy is wet. Unfortunately, we didn't have a wetness sensor to determine when the canopy was wet and when the canopy was dry. So just to provide some summary in conclusion, canopy temperatures can be used as a means to determine plant canopy water status. There's multiple ways to do so. I've demonstrated a simple and a more complex method for using canopy temperatures to estimate water status. We found that both methods were sensitive to water stress and rainfall. And maybe the most important conclusion that I can make is that in order for the methods to work, the canopy temperature measurements must be accurate. So the correction for surface emissivity is significant and should be done, and field of view must be considered, especially for conditions of partial canopy cover. We want to make sure that canopy is being measured rather than some mixture of canopy and soil. Here are the references for the papers that I mentioned during the talk. Much more detail can be found regarding the 3 different methods in each paper. I hope this presentation was helpful for everyone. I really appreciate the opportunity to be a part of Decagon's seminar series, and I thank the audience for their participation.